Hello students, myself Professor Jayesh Prajapati. Today our topic is a three-phase inverter or a six-step inverter. Let us start. Today the question for a day is how to obtain a three-phase AC supply from a DC supply. We already know that the DC supply waveform is like this, and we have to convert this DC supply into a three-phase sinusoidal AC supply. That is a waveform for three-phase AC supply. The three-phase AC supply having a three-phase, that is R phase, Y phase and B phase. These three phases are 120-degree phase shift with each others. That is a three-phase sinusoidal AC supply. Now we have to convert this DC supply into a three-phase AC supply. So the solution for the question is a three-phase inverter. A three-phase inverter is a device that can be used to convert this DC supply into a three-phase sinusoidal AC supply. In this today's session, we will discuss this three-phase inverter. Okay, let us start with a classification of inverter. Classification of inverter. Inverters basically can be classified in two ways. First, according to the output waveforms, and second, according to the types of load. According to the output waveform means whatever the waveform is come at the output, it can be classified in three manners. First, that is a square wave inverter. Second, that is a modified sine wave inverter. Modified sine wave means what? A quasi-square or a PWM wave, that is a modified sine wave inverters. Then sine wave inverters. So according to the output waveform, it can be classified as a square wave, modified sine wave and sine wave inverters. Now according to the types of load, it can be classified in two ways. A load may be a single phase or three phase, so it can be classified as a single phase inverter or a three phase inverter. And a single phase inverter is also classified in two ways, that is a half bridge inverter and full bridge inverter. And a three phase inverters can be classified also in two ways, that is a 120-degree mode of conduction and a 180-degree mode of conduction. In today's session, we will discuss this three-phase inverter and the mode, that is the 180-degree mode of conduction. So in this today's session, we will discuss this three-phase inverters. So that is the classification of the inverters. Let us start with the three-phase inverters. Okay. That is a circuit diagram for a three-phase inverters. In this circuit diagram, you can see that is the input DC supply and that is the output A, output B and output C. That means R phase, Y phase and B phase. These three phases we can get at the output. So that is the input and outputs. For obtaining a three-phase AC supply from a given DC batteries, we will use a 6 thyristor. Here we can use thyristor at that means HCR, silicon control rectifier, that is Q1, Q2, Q3, Q4, Q5 and Q6. So here the power semiconductor device is HCR. So here we can use a 6 thyristor and 6 diode D1 to D6. Okay, so this 6 power semiconductor device and 6 diode are used. These diodes are feedback diodes. Diode can be classified according to the application. It can be a rectifier diode, that is a normal PN junction diode that can be used to convert AC signal into a DC signal. And second, that is a freewheeling diode. We already know that a freewheeling diode is always connected across the inductive load. Okay, and it will release the energy through the diode, that is a freewheeling portion. And here we can use, that is a diode, that is a feedback diode. Feedback diode is always connected across the power semiconductor device. So here we can connect this diode across the HCR. And feedback diode is used in inverter, that means it can be used in DC to AC converters. It can be used in DC to AC converter. Inverter means what? It converts a DC supply into AC supply. So feedback diode is used in DC to AC converter across a power semiconductor device to return back the stored energy to the DC supply. Feedback diode function is what? To return back the stored energy to the DC supply. Okay, so that is a feedback diode and freewheeling diode and rectifier diode. Now here load will be connected across A, B and C. A load may be a resistive or inductive in nature, and it can be connected in star or delta configuration. So here we cannot connect a load here, but it can be connected like a star configuration or data configuration. If we have to see this in a simple manner, so let us see with the load connected. So here you can see in the circuit, here we can connect the load across A, B in C. Okay, A, B and C. Here we can connect the load as a resistive load in star connect configuration. Okay, so load may be connected in this manner. So that is figure is only for understanding. We have basic, our main figure is this. Okay, okay, now the switches are, these switches are turn on and off at regular interval of 6 interval. The sequence of on and off is programmed to obtain a three-phase voltage. If we have to get a three-phase voltage, then we have to give the gate driving signal. We already know that HCR having a three terminal, that is anode, cathode and that is a third terminal, that is a gate terminal. So in the third terminal we have to give the control signals. Okay, so depending on the types of control signals, applied to the thyristor, it can be three-phase inverters can be obtained in a two mode of operation. It can be a 180-degree mode of conduction and 120-degree mode of conduction. In 180-degree mode of conduction, each thyristor is remains on for 0 to 180-degree mode, and in 120-degree mode of conduction, each thyristor is remains to on for 120-degree mode of conduction. Means what? In 180-degree, a thyristor remains on for 0 to 180-degree, and in 120-degree, a thyristor remains to on for 0 to 120-degree. Okay, in three-phase inverter, at any given instant of time, three thyristor will be conduct simultaneously. In this circuit diagram, we have seen 6 thyristor, but in every interval, it have a 6 interval. So in the every interval, a 3 thyristor is remains to be on in every interval. Okay, now in 180-degree mode of conduction, after every 60-degree, one of the conducting thyristor is turned off and the other thyristor comes into the conduction. Means after every 60-degree, one of the thyristor is turned on and another thyristor is turned off. We have seen this in the waveforms. Okay. In today's session, we will study a 180-degree mode of conduction. So let us start with 180-degree mode of conduction. In the 180-degree mode of conduction, we have to draw the gate driving waveforms. So we have to draw the gate driving waveforms. So circuit operate in 6 steps. Each step is 60 degrees. So we have draw the waveform like in this way. Each step is a 60 degrees. We have drawn 0, 60, 120, 180, 240, 300 and 360. Means we have used 0 to 360, means a wall cycle, 0 to 2 pi. Okay, in the wall cycle we have drawn the waveforms. Okay, each thyristor is operate after every 60 degree and remains on for 180 degree, because this is a 180 degree mode of conduction. Now starting with a thyristor Q1, it is fired at alpha is equal to 0 and conducts still at alpha is equal to 180 degrees. You can see it is on for 0 degree and remains on for alpha is equal to 180 degrees. Now when Q1 is on, Q2 will be fired at alpha is equal to 60 degree and remains on for 240 degrees. You can see alpha is equal to 60 degree, it can be on and it can be on for 240 degrees. So here this portion is 180 degree, it can be remains on for 180 degrees. Okay, because of 180 degree mode of conduction. Now Q3, similarly Q3 can be on for alpha is equal to 120 degrees mode of conduction. So you can see then Q4 will be on for alpha is equal to 180 degree and it can be remains on for 360 degrees. So that is a Q4, and Q4 then Q5 is on for alpha is equal to 240 degrees and Q6 is on for alpha is equal to 300 degrees. Here the sequence is continue for another cycles for 360. After 360 it can be continue for this. Okay, we have only seen for one cycle. Okay, now here that is a gate driving waveform for Q1 to Q6. Okay, in this waveform you can see here we have seen that is a mode 1 0 to 60 degrees, then mode 2 60 to 120, 180, 240, 300 and 360. So in the first mode, that is a 0 to 60 degree mode of conduction, you can see in this session the Q1 is on, Q5 is on and Q6 is on in 0 to 60 degrees mode of conduction. So we can say that in the mode 1 thyristor Q1, Q5 and Q6 is on. So thyristor 1, 5 and 6 is on in this mode of conduction. Okay. Now in second mode you can see Q1 on, Q2 on and Q6 on. So we can say that in this mode 1, 2 and 6 is on. Similarly in the third mode, that is 120 to 180 degrees, Q1, Q2 and Q3 is on, 1, 2, 3 on. In the fourth mode 4, 2 and 3 is on. In the fifth mode thyristor 4, 5 and 3 is on. In the last mode, that is a mode 6, 4, 5 and 6 is on. So that is the sequence pattern. That means step 1, step 2, step 3 and step 4 and step 5 and step 6. That means a thyristor having a 3-phase inverter having a 6 step. Each step having it in every step you can see a 3 power semiconductor device is on, means 3 thyristor is on in every interval. Okay, simultaneously. Okay, not a same but it can be on like simultaneously. So we can say that that is a mode 1, that is a mode 2 that is a mode 3, that is a mode 4, that is mode 5, and that is a mode 6. So it having a 6 step. So the pattern is repeat for the further cycles. We have only discussed the 6 modes. Okay, so it is also called as a 6-step inverter. Why 6-step? Because it having a 6-step. So in this 6-step, so it is also called as a 6-mode inverter or a 6-step inverter. Okay, now we have to see the circuit what respond during this every mode. So first of all, we will study the mode 1. Okay, now study the mode 1. We know that in the mode 1, 1, 5 and 6 is on. You can see that is a mode 1. In mode 1, the thyristor, that is 1, 5, 6 is on. Okay, so in this mode we know that that is a 0 to pi by 3, that means 0 to 60-degree mode of conduction. In this mode, the thyristor Q1, Q5 and Q6 is on. So we have to close this circuit. Here 1, 2 and that is a 1, 2, okay, 1, 5 and 6. We know that in this mode, thyristor 1, thyristor 5 and the thyristor 6 is on. So we have closed this switch, and here you can see the thyristor 1 and 5 that is connected to the positive terminal of DC supply. A DC supply having a two terminal, positive and negative terminal. Okay, and the 6 is connected here with a negative terminal. So we can say that the terminal A and the terminal C. Okay, so the terminal A that is connected to the positive supply and the terminal C that is connected to the also positive supply. That means A and C is connected to the A and C that is connected to the positive supply. You can see C is connected to the positive supply and also A terminal is also connected to the positive terminal, but that is a 6, that is a B terminal. B terminal is connected to the negative terminal of DC supply. Okay, so from this figure, if we have to draw the equivalent circuit, so its equivalent circuit is like this. Okay, in the equivalent circuit you can see A terminal and C terminal that is connected across the positive terminal of DC supply, and B terminal is connected to the negative terminal of DC supply. Now also from the figure you can see a one thyristor number 1 and 5 is triggered, and this two resistive load is in this two resistive load in parallel combination with this third resistive component. Okay, so we can say that in the equivalent circuit the terminal A and C is parallel in series with the terminal B. Okay, you can see the terminal R and this resistor R are in parallel combination with this resistor R. Okay, now if we have to find the equivalent resistance from this figure, then the equivalent resistor is the parallel combination and this series combination, that is R plus R by 2. That is the equivalent resistance, that is R plus R by 2, that is 3R by 2. Now if we have to find the current I1, then the current I1 from Ohm's law, it can be a voltage Vs divided by the equivalent resistance of these parallel combinations. Okay, if the parallel combinations, so the equation for the I1 is equal to Vs divided by equivalent resistance, and the equivalent resistance is 3R by 2. So we can write 2Vs divided by 3R. Now, if we have to find the phase voltage, here we know that is a phase voltage AN, phase voltage Cn, then phase voltage Bn. So we have to find this phase voltage. So phase voltage AN and phase voltage Cn are same, because we know that is a parallel combination, and the in the parallel circuit the voltage are same but the current are differ. So we can say that the voltage AN and voltage Cn are equal. So we can write here like VAN is equal to VCN is equal to I1 into the equivalent resistor of these combinations. Equivalent resistance of this combination, that is R by 2. So we can write I1 into R by 2, that is Vs by 3. VAN is equal to VCN is equal to Vs by 3. And the last, that is a phase voltage BN, VBN. We know that the VBN is connected to the negative terminal of DC supply. So here we can write VBN is equal to negative I1 into the resistor is R. So we can write VBN is equal to minus I1 into R. So the answer is minus 2 Vs by 3. Okay. So we have find in the mode 1, that is a phase voltage AN, BN and CN. AN, CN are similar, and then VBN. Okay. Now similarly we have seen the mode 2. Okay. Now in mode 2, that is a 60 to 120 degree mode. We know that is a mode 2, that is a 60 to 120 degree mode. In this mode the thyristor 1, 2 and 6 are on. Okay, so let us go to the our slide. Mode 2, that is in mode 2 thyristor Q1, Q2 and Q6 is conduct. So we have to draw the main circuit. In the main circuit you can see a thyristor 1, 6 and 2 are on. So you can see the first thyristor connected to the positive terminal of DC supply, and the second and 6 thyristor number 2 and thyristor number 6, that is connected to the negative terminal of DC supply. Okay, and also the terminals also you can see the terminal A. We can say that a terminal A that is connected to the positive supply of DC supply, and this two terminal B and C, these two terminals are connected to the negative terminal. Okay, so here we can draw, if we draw the circuit diagram, then in the equivalent circuit diagram B and C terminal is in connected to the negative terminal, and A is connected to the positive terminal, and A is in series combination with this two parallel combination of B and C. Okay, so if we have draw the equivalent circuit for this circuit, then equivalent circuit is like this. B and C terminal is connected to the negative supply, B and C terminal is connected to the negative supply, and the A terminal is connected to the positive supply, and we say that the thyristor 1, 2 and 6 is conduct in this mode of conduction. Now Similarly, we have to find the equivalent resistance. Then the equivalent resistance is this combination is a series resistor R and this parallel combination R by 2, that is 3R by 2. And if we have find the current I2, then I2 is equal to Vs divided by equivalent resistance, that is similar to the mode 1, 2 Vs by 3R. Now here we have to find the phase voltage. So first of all we have find the voltage, that is we have seen that phase voltage AN, then phase voltage Bn, and voice voltage Cn. But in this case you can see the phase voltage Bn and voice voltage Cn are same because this is a parallel combination. In the parallel we know that the two phase voltage are same, and here the phase voltage, that is VAN. So first of all we have find the phase voltage VAN, that is equal to a positive I2 into resistor R, that is this resistor R, that is this resistor R, okay, and that is a current I2. So we can write I2 into R, that is equal to 2 Vs by I. This is a I2 and we have to cut this resistor R, so the answer is 2 Vs by 3. Okay, now here the phase voltage VBN and phase voltage VCN, that is same, but it is connected to the negative terminal. So here we can write VBN is equal to VCN is equal to negative I2 into the resistor of this combination, that is R by 2. Okay, so the if we have to find the answer, then the 2 also cancel, 2 also cancel, and the R also cancel. So the answer is minus Vs by 3. So in this case mode 2 phase voltage is 2 Vs by 3 and this two phase voltage are minus Vs by 3. Okay, now similarly we have entered in the mode 3. In mode 3 you can see that is a mode 3, that is a 180 degree to 120 degree to 180 degree mode of conduction. You can see here the thyristor 1, 2 and 3 are on. So in this mode 3 operation, that is 2 pi by 3 to pi, that means 120 degree to 180 degree mode of conduction. In this, if we have draw the circuit, then in this circuit you can see the thyristor 1, thyristor 3 and thyristor 2 are on. So 1 and 3 that is connected to the positive terminal, that means the terminal A and terminal B that is connected to the positive supply. Okay, and the terminal C, that is the terminal C, and the thyristor 2, that is terminal 3, that is connected to the negative supply. Okay, now from this if we have draw the equivalent circuits, the equivalent circuit is like this. A and B terminal is connected to the positive supply, A and B that is connected to the positive supply, and the C terminal that is connected to the negative terminal, and this two parallel combination, and that is a series combination. Okay, uh, so similarly here have find the equivalent resistor, that is the same R plus R by 2, that is 3R by 2, and the current is also same, Vs divided by R by 2, that is 2 Vs by 3. Now here we have find the phase voltage AN and phase voltage BN. So you can see the phase voltage AN and phase voltage BN that are same, and the current that is I3, and the resistor of this combination that is R by 2. So VAN is equal to VBN, that is equal to I3 into R by 2. Okay, and VCN, that is equal to negative minus 2 Vs by 3. Similarly, we can solve these equations of previous sem. Now in this 1 2 3 and 1 mode 1 2 and 3, similarly the pattern is repeated for mode 4 5 and 6. So we here we have only draw the graph tables. Okay, so in the tables we have mentioned the all modes. Okay, and here we have mentioned in the tables, you can see we can mention the phase voltage AN, BN and CN in every mode: mode 1, mode 2, mode 3, mode 4, mode 5 and mode 6. Okay, and you can see in the mode 1, we already find this in the mode 1, that is mode 1. We have find this you can see VAN and VCN, that is Vs by 3, and you can see that VAN and VCN, that is V by 3, and VBN, that is minus 2V by 3. And similarly every mode we can enter here. Okay, so in this also we have okay, that is mode 3. Now okay, in this table we have mentioned this phase voltage and line voltage, phase voltage AN, BN and CN. Okay, now the line voltage means what? Line voltage means that is a one phase, that is second phase, and that is a third phase, and that is a neutral line. So here we can write that is a R phase, that is Y phase, and that is B phase, and that is a neutral. So here that is a terminal, that is a B terminal, and that is a C terminal, and that is a neutral terminal that here we have taken. So the if we have take R and neutral, that is a phase voltage, and if we have draw this line, then it is a line voltage between A and B, or between R and Y phase. So that is a line voltage and that is a phase voltage. So that is a difference between a line voltage and phase voltage. Okay, uh, now in this figure we have draw a table. In this table you can see we have used a line voltage and phase voltage. So a line voltage means what? VAB is equal to VAN minus VBN. So if we have minus V by 3, then minus minus plus 2 V by 3, then the answer is V. Similarly VBN is equal to the VBN minus VCN. So similarly you can get this line voltage from this phase voltage. Okay, so this table is very useful. In this table we have find every mode, phase voltage and line voltage. Now we have to draw the waveforms for phase voltage and line voltage. So in this phase voltage and line voltage waveform, uh, we have draw the extend line here. You can see we have draw the extend line, and we have also entered the degrees, that means 0 to 60, 120, 180 and 240. Now we have to just only draw the waveforms. So phase voltage, these are the phase voltage and these are the line voltage. So if we know the values, then you can draw the waveforms easily. So for this example, we have only draw the waveform for phase voltage AN and for line voltage VAB. So let us start with we have to draw the waveforms. So we have first draw the waveforms graphs 0 to 360 degrees, and that is a phase voltage VAN, then that is a line voltage VAB. In the first mode, 0 to 60 degrees, we know that 0 to 60 degrees, the VAN is equal to V by 3 and VAB is equal to V. So we draw VAN that is equal to V by 3 and VAB that is equal to V. Okay, we have draw V, that is a positive V. Now in second mode, that is a 60 to 120 degrees, 60 to 120 degrees, the phase voltage VBN that is 2V by 3 and the line voltage that is V. So we have to draw in this 60 to 120 degrees, that is 2V by 3. So we can take a higher position, that is 2V by 3. And here 60 to 120 line voltage is same. So we can draw the line same. Okay. Now third mode. In the third mode, you can see in third mode, VAN is equal to V by 3 and VAB is equal to 0. So similarly, we have to draw the waveform. The waveform for mode 3, that is 120 to 180, that is V by 3 and the line voltage that is 0. So in this 1, 2, 3 mode, the waveform is like this. Now in the mode 4, you can see mode 4, the VAN is equal to minus V by 3 and line voltage is minus V, and also we have remember that is mode 5 minus 2Y by 3 V by 3 and the VAB is minus V, and in mode 6 you can see minus V by 3 and here is 0. So similarly, if we have to draw the waveform, so you can see the mode 4, that is 180 to 240 degrees, that is we have drawn minus V by 3 and a line voltage that is a negative V. So we have drawn in this way, and in mode 4, that is a 240 to 300 degree mode of, so here we can draw minus 2V by 3 and line voltage that is also similar minus V, and the mode 6 you can see the waveform is minus V by 3 and the line voltage is 0. So in this way we can draw the waveforms for phase voltage VBN and phase voltage VBN CN and line voltage VBC and VCE. So similarly you can draw the waveforms for this. So here you can see the phase voltage is in 6 step. Okay, that is a step 1, step 2, step 3, step 4, step 5 and step 6. So here a step waveform. So it is also called as a 6-step inverter, and you can see the final average value, that is a sinusoidal AC supply. Okay, so you can get a sinusoidal in step manner. So you can get a 3-phase. Okay, we have only draw the phase voltage 1. You can also draw a phase voltage VBN and VCN. So you can get a sinusoidal 3-phase AC supply, and you can see the line voltage that is a positive and that is 0 and that is negative. That means it can be a quasi square wave waveform. You can say the line voltage waveform is a quasi square wave waveform and phase voltage waveform is a step waveform, 6-step waveforms. Okay, so in this way you can get draw the waveforms. Okay, and if we draw the wall waveform in the one page, then that is a gate driving waveforms. You can see gate driving waveform for thyristor 1 to thyristor 6, that is IG1, IG2, IG3, IG4, IG5 and IG6. That is a gate driving waveform, and this cycle is 0 to 180 degree cycles. Okay, so here you can see transistor thyristor 1, 5 and 6 on in the second mode, 1, 2 and 6 on in the third mode, 1, 2 and 3. So similarly we have drawn this waveform in one page also, and here we have drawn the line voltage VAB, line voltage VBC and line voltage VCA. You can see that is a quasi square waveform. Okay, every line voltage. So you can draw this waveform in this way also in one pages. So that is a 180-degree mode of conduction. Now applications. What are the application of these inverters? So it having a application like a uni interrupt power supply, UPS, that is a power backup. Okay, in the UPS you can store some energy and it can be utilized by AC supply. So basically in UPS it is a battery charger. So in the to convert a DC supply into AC supply, the inverter circuit is used in a UPS, that is the uni interrupt power supply. Then second most important application is a three-phase AC motor speed control. If we have to speed control of three-phase AC motor, then V by F speed control technique is also used to control the speed of DC motor. So in this case, we have to first convert AC into DC and then DC into AC. So we have get a variable DC, variable AC, that means frequency change can be done by the inverters circuit. So second most application, and the most MP application is a solar power system. We already know that in the solar power system we can store solar radiation, PV rays, and we have get this PV rays to the store in the batteries in DC plus and minus terminal. Then this DC is converted into AC and it can be utilized in the system. So if we draw the circuits, in the circuit you can see that is a PV solar panels, and that is a, inverter circuit, and here you can get a DC to AC. Here you can get AC supply. You can see that is a solar panel and that is a three-phase inverter circuit, and here you can get a three-phase AC supply. Okay, so in the solar power system a three-phase inverter circuit is also useful. And variable frequency drive we have already discussed, that is a three-phase AC motor speed control. You can see here we have a constant frequency motor speed drive. So here the signal is AC supply. Okay, AC supply signal, and AC is converted into the DC, that is by rectifier, and this DC is given to the inverter. So inverter convert DC into AC. So here a constant frequency, but here we can get modify and variable frequency. Okay, so here the frequency is like this, and here you can see the frequency is like this. That means variable frequency drive, you can use a inverter circuit in variable frequency drive. Okay, thank you for listening me.